in the last segment we talked about the relationship between the weight that is getting applied onto a beam, the transverse load basically on a beam, and the resulting shearing force and the resulting bending moment. We saw that and we came up with this relationship that your dV over dx is depending on x. Similarly, dm over dx is your v of x, right? Now, and before that, in I think the previous segment of this, or even before that, we had derived an equation under the pure bending case that 1 over rho is m over EI, right? That means this rho is the radius of curvature of the arc which results in when you apply a pure moment of bending. Okay. But then we discussed about the fact that though in a condition where shearing force also exists, where it is not a case of pure bending, still segment by segment we can think of that segment as where a moment of the value at that location, whatever is that location's m value is, mx, if you think that is getting applied, then you can also think that the rho is also a function of x, right. So, that is the basic idea. So, at any location, suppose if it's a beam and it is a is like this, hinged at these 2 points, and forever you are applying a load like this. Okay. Now, it will bend, it will take a shape, but at any location, say from here at a distance x, m will have some value, and if you pick a small segment here, you can consider that that segment is subjected to the bending moment at that location, and under that it is taking the shape of a circle, and then the radius of curvature at that location will be given by this equation. But then we also know from differential geometry that your radius of curvature, the curvature, okay. So, 1 over rho, I will write it here only. So, 1 over rho is, if it is a general form when a function y is given as a function of x like that. So, at any location the radius of curvature, so this is say rho, okay. Now, that so the curvature's formula you know from your 12th standard thing that it's like this, and 1 plus dy of dx whole square raised to 3 over 2, right. So, this is the information which you have got from your previous knowledge of differential geometry. But then we are, if you remember, we are considering deflections which are very small. Nowhere we are getting a lot of deformations, because otherwise the linearity which we have assumed between the stress and strain will not be validated, and that is why dy by dx is always very small as compared to unity, and here in fact it is even squared. So, the value is even getting smaller. So, this denominator can simply be neglected, and you have, I'll again say take these things a bit to the left side, and then okay, now I'll write it here only so that it will be okay. So 1 by rho can be now safely approximated like this, and which will come and sit here. So your d square y over dx squared is m over e I. Okay. So generally this equation is written in this form. Everywhere you will see mostly in this form. Whatever, I mean, because you can assume that E is constant, I is constant. If you this equation is valid when E and I are also functions of x. Okay, so in that case you can keep it like that. So can I write them explicitly? Okay, I'll write them explicitly there. See, m here is a function of x, and similarly E can be a function of x, and I also can be a function of x. So that's the most general form. But if I and E are independent of x, which will be most cases for your problems, so the equation is written like in this way: m is a function of x. Okay, so but this is the most general form of the equation, right? Now if you have this equation, then what you can do, you can, if you solve this differential equation, you can always figure out y is a function of x, which will be nothing but the deflection curve of the beam under this particular load, right? And how the load has come to affect m, you know that you have applied some load which has resulted in some shear force which varies in some particular fashion, and that tells you how the bending moment varies with respect to x, and that shape or profile of bending moment now is dictating the radius of curvature or curvature at every location, right? And depending on the flexural rigidity. Okay, so this we had discussed that this is the flexural rigidity. That means based on both material and geometry, the moment of inertia of the cross section. Okay, so based on that, the curvature will be defined. And then what you can do is you can integrate once this formula to get, say, dy over dx to be equal to what? Your m as a function of x dx integral, right, say from 0 to x plus some constant c1. Okay, now you can, once you have integrated this, and again if you integrate this, so here again I am assuming that E and I are constant, so they have come out like this. Otherwise you could have kept it there and then you could have integrated the full function. Anyways, so now this as a function of x, now I am writing explicitly, is nothing but you integrate this as m x dx, okay, 0 to x, 0 to x. Now here you have c1 times dx, right, because yeah, c1 dx integration plus c2. Fine. So that's the formula which you can get for this. Great. Now the question is, this is quite straightforward. there is no issue about that. But the thing is, what about these two constants, okay, this and this? So that if you can evaluate under a given condition, and then you are done. M, you know how to get it from the shear force bending moment diagram, or by applying the differential equation. From the load you can calculate that, then put this and integrate it and done. Only thing now to be to notice about is the constants C1 and C2 and how to evaluate them. They will be evaluated based on the boundary conditions. What I mean by that is, I'll just draw three cases which are primarily of our concern for this subject, for this course in this semester, and they are of these types, One is called a simply supported beam. So here it's hinged, okay, and here also it's hinged, and the beam is like that, and the loading could be anything, okay, or I'll just draw it in. Loading could be anything. That's called simply supported. Then another is of say overhanging type, again, but the supports are again say like this and hinged at this location, okay. So simply supported means these ends, the joints at the ends, they are not able to apply any twisting effort on the beam. They are hinges, free hinges, okay. Similarly here, so free hinges, so they cannot twist the beam, they can just support the motion in the y direction. And then again you have your it's bad, okay, again loading, whatever is the load, like that. And the third case, which will be like this, and we have say a cantilever beam. That means one side of the beam is completely fixed to the wall. Now in these three cases, why they are simple and why directly you can solve them is, you get two very well defined boundary condition in all these three cases, which if you apply to these differential equations, you will be able to get these constants and it is done. Now what are those boundary conditions? See here, at x is equal to 0, y is 0. So that's one condition. And say x is equal to L, y is equal to 0. So that's the case condition. And so now you just think about this equation. This is the case where you have integrated it to get a function of y, function y of x, and two constants sitting there, right? In fact, this one will just become C1x type plus C2. Then you put this once, you get one equation between C1 and C2, then you put this condition again on the same equation, you will get another equation between C1 and C2, solve them, you get the values of C1 and C2. And exactly the same way, here it's at x is equal to 0, y is 0, and here x is equal to some xl, okay, that is not the full length of the beam, and again at the same thing y is equal to 0. So that means this will become 0, and again the same thing, you put this condition once to get one equation, put this condition again to get another condition, and done. Now coming to this sort of thing, what you can do is at x is equal to 0, y definitely is 0, but then the other condition is at x is equal to 0, dy over dx is 0. That means at this location the bend will happen in such a way that the slope has to be 0 at that location. It can just bend like this. but if you see the slope here, it has to be 0. There it cannot have any slope. So that gives you the second condition, and so this first type you can apply here, but for this second one you have to go and apply it here, because you have the condition here, dy over dx. Okay, so whatever value here, so the 0 you put here and you get this c1. So first you apply this to get the value c1, and then you apply this and you know now c1 already, so get the value of c2 and it's done. So that is how, once you figure out c1 and c2, you are having the complete deflection equation. That is the function y as a function of x. So that's about the deflection of beams, and everything what we have discussed are for Euler beams, where the deformation of the full beam is happening only because of bending. No shear stress is causing any deformation whatsoever. Okay, under that condition, that is Euler-Bernoulli beam. Okay, so these are the equations which you can use to find out the deflection curve. Very good, then that's fine. See you in the next segment.